Okay. Oh, shall I go? All right. So firstly, welcome to the seminar today. Before starting, I'd like to acknowledge the Ngunnawal people as traditional custodians of the land where we meet and recognise other people or families with connection to the lands of the ACT and region. I acknowledge and respect their continuing culture and the contribution they make to the life of this city and the region. I think I got that from a different place to typical one, but yeah, it covers everything. So look, first of all, thank you to you all for coming. Today we have a seminar by Dr. Fanny Garel, who is a leading geodynamicist whose work explores the physical processes driving the evolution of Earth's surface and interior across geological timescales. So Fanny applies the principles of fluid mechanics, heat transfer, and solid deformation to tackle key questions in tectonics. I'm going to put this down somewhere, sorry. In tectonics and mantle dynamics, from subduction to lithospheric deformation to the evolution of plate boundaries. So Fanny completed her PhD at, I'm going to say IPGP because my French is shocking, in 2012, focused mainly on the dynamics and cooling of lava flows. She then moved to the UK to work with Hugh Davis at Cardiff, Saskia Ghosh at Imperial, and myself. I was actually my first postdoc, working on the dynamics of subduction. So really combining state-of-the-art adaptive mesh numerical models, which, to be fair, had never been applied to subduction dynamics before, so there's a lot of work. But looking at the dynamics of subduction and comparing the model predictions with observations, principally from seismology and gravimetry. Look, for me, as my first postdoc, it was a formative experience. I learned an awful lot from Fanny. And actually continued to do so. I think for Fanny, it was formative in a different way because she only did 2 years of postdoc and immediately stepped into a continuing position at the University of Montpellier, which really, I guess, is a testament to the quality of her PhD work and postdoctoral work. Where am I? I'm about 4 paragraphs in. Since 2014, you've been at the University of Montpellier, and this is actually quite striking for everybody in the room. So Fanny not only has a young family, but manages a very, what I would call, excessive teaching load of over 200 contact hours per year, and still manages to maintain kind of a world-leading research program. So it's a bit of an eye-opener for me, that. And look, since 2022, you lead the, I'm going to read this out because this is a very interesting project description. The REOBreak project. So it's a project which is equivalent to kind of a 5-year future fellowship in Australia. And that project is called REOBreak. It investigates how the Earth's mantle can slowly flow and deform over time, and how this behavior governs the breaking and shifting of tectonic plates at the surface. It combines cutting-edge models with geological and geophysical observations to understand why plate boundaries form where they do, how the deep Earth controls the architecture of the planet's surface. And it's a project with big scientific ambition, one that I would argue, and hopefully you'll all agree by the end of the talk, reflects Fanny's creativity, rigor, and deep curiosity about how the planet works. Those of you that were here in 2014 may remember Fanny. It's actually her second visit to the ANU.
2013.
Sorry, I had kids at that time. I don't remember much. But yeah, so Fanny came in 2013. This is the second visit, but this is a bit longer. So this is a formal sabbatical. She's been here for 5 months and I think has 1 month to go. And look, I think I speak for everybody that's interacted with Fanny. It's been a real pleasure to have you here. We're all very grateful for your input, your discussion, your humor, your enthusiasm, all of the love you show for science and the advice you've given a lot of people in this room. So thank you for coming back. I'll hand over now. And today Fanny's going to talk about the generation of deep earthquakes in subduction zones. Over to you.
Thank you. Well, thank you very much, Rodri, for this introduction, and thank you for having me here. So this year I have teaching leave, yes. I'm really happy not to teach this year, even though I will be happy to go back to teaching next year. And yeah, I'm really happy to be here at the ANU, which is both at the RSES, which is a historical lab where so many discoveries had been made. So I'm next to the Ringwood room, and it's quite moving for me because I work in the transition zone of the mantle. So it's interesting, and thank you as well for your warm welcome. It's been really nice on a personal and a scientific level, and I still have 1 month left to do everything I said I would do. So I'm working, of course, with Roger as well, but also with a bunch of people from Montpellier, from my postdoc, and from elsewhere. I'm going to focus today about the deep earthquake and what we can learn from dynamical, subduction dynamical models about them. But as Rodri said, I'm also interested in the deformation of core plate for the formation of plate boundaries at the surface, which I will not discuss much here, but yeah, that's the same. That's the same rheology and the same dynamical model. I wanted to start here by showing these two historical and then more recent seismicity world map, because it's really how we define the plates. It's not the actual plates that we see, it's the plate boundaries. So we're used of thinking of earthquake as at the boundary of plate, not within the plate, and we generally view seismicity as a how do you say, as a manifestation of deformation at weak plate boundaries, whereas where there is no or very little seismicity, it indicates the plates that are mechanically resistant. But that changes a bit in subduction zone. And you can see here, we already see subduction zone because this is where the deep earthquake occur. So I will touch a bit more about this deep earthquake here. So the earthquakes are not only at the surface, at plate boundary, they also occur at depths and probably most of them within the plate. So the historical observations that were published by Kiyo Wadati, so he looked at the difference in S wave and P wave travel times that are much different from a shallow event than for a deep event. So he was able to say, okay, we have really deep events, more than 300 kilometers, even up to 500, he said in his early publication in the late 20s and 30s. So there are deep earthquakes at subduction zone. This was confirmed in the following decades with this historical paper by Hugo Benioff, hence the Wadati-Benioff zone that we usually trace looking at deep seismicity. And so that was, the seismicity was indeed quite deep and was happening, well, around nearby the subduction trenches. So the question was, what is the mechanism of this deep earthquake? So Benioff in this paper said, oh yeah, there is a great fault. Okay, so is that our classical faulting rupture? People have been working on that ever since, but it's always nice to see that we can publish some observation, even though we don't understand the mechanism. And so deep earthquake have been focused on since the late 20s. So where are they located? So after with the progress of seismic imaging, it's not only about locating the earthquake, we can also locate the seismic velocity anomalies. And here I show you two cross sections, so one near Japan, South Japan, and one in near the Marianas, saying that a lot of seismicity is indeed inside the slab, inside what we think is the cold plate, with the fast velocity anomaly, but it's not necessarily right in the middle. So I won't talk about the intermediate depth earthquake for which a double Benioff zone have been imaged. I'm really talking about the deep focus earthquake deeper than 300 kilometers. And some of them are directly inside the cold slab, but some of them seem to be on the edge of the slab. So I will come back to that later. So it seems that temperature will not be the only control, but these earthquakes are happening within the slab within the cold plate. So it's very different from the surface earthquakes that are happening at plate boundaries. So why do we have earthquake deep in the mantle? Why now the idea of a great fold has been forsaken? Because it's not the classical rupture mechanism. So we used to think of earthquake. So here I took this image from Australian earth science education. So we accumulate strain, and after some point, elastic energy accumulates, and after some point, it exceeds the mechanical resistance, and a fault creates. So it's the I can take, for example, this analog material. So this comes very nice for education and for students and children. So it's a bouncing putty. So if I strain it too much, I will, oh, this is called, okay, I have to go faster for the rupture, up. Okay, so I can accumulate strain and then break it. These are the classical. So if I increase stress to a point, I will then have a rupture, first elastic and then brittle. But remember, we are located quite deep in the mantle. So our rock, our beautiful upper mantle rock. Thank you, Olivier, for lending me this peridotite xenolite. So the mantle is green. Don't color it as orange or red, even though deeper we're not sure of the color actually. But as we go to the depths, pressure and temperature increases, which means that we're not in the brittle failure regime anymore, because when we increase the confining pressure and also when we increase the temperature, we go to a creep, a ductile regime, okay, without adding any additional stress. There is still a deformation of the rock. The rock flows, okay, it's the creep. So it's not our classical rupture, it's more something creeping, something that we could define as viscous somehow. And I point again this historical experiment of the rubber band. So it started to sink in 1982. You can see that at Questacon. So it took about 10 years to reach the bottom, and now it's gently spreading. So it's like this putty. So if I let it here evolve, by the end of the seminar, it will have spread. It's a bit cold, but you see this one I have left in a plate and it has spread as well. So this putty has really the same mechanical properties as the peridotite. It's both elastic, I didn't say, but it bounces. Bounces too much. Okay, so it's elastic and seismic waves can come through, it's brittle, and if you wait long enough, it will be viscous. So I'm interested in that scale of deformation. And here, so I really like this diagram. It's the idea really we have a continuity. So even though I will be talking about earthquake, so short time scale, and well, the length scale can be discussed, but this happens on short time scales. This is related. It's a continuum to the large time scales with subduction, mantle convection, and plate deformation. And I'm also going to try to use some small scale flow laws, creep laws, to apply to the mantle dynamics. Okay, so what mechanisms have been proposed for this earthquake so deep in the mantle, if it's not a rupture? There are several mechanisms that have been proposed. So experimentalists are looking into that. I don't know all the details, but basically several processes have been proposed. So in relationship to the metastability of the olivine alpha that is supposed to transform into Watt's-Leigh below 400 kilometers, but that don't always transform, we think, from seismic imaging as well. So could that metastability and then olivine transform into Watt's-Leigh or Rigwoodite cause some transformational faulting? Okay, so this paper here, I won't go into the details, but maybe that seismicity is located on the edge of the metastable wedge. It has also been proposed that it could be due to dehydration reactions. So change in volumes will cause enough stress to create a mechanical rupture that could then propagate. This is the mechanism proposed for intermediate earthquake with the two Benioff zone explained by the dehydration of both the mantle and the crust. Also, people have proposed the mechanism of thermal runaway when we have a grain size evolution. So strain rate evolves with temperature, and we have a boundary between a stable system and something where both temperature and strain rate will increase a lot up to the point of mechanical rupture. This is due to grain size evolution that depends also on strain rate. So basically, whatever the mechanism, it seems that we're looking for both quite low temperature, because we need the kinetic reaction, kinetic transformation of olivine alpha into Wachsleite beta or into a Regunite gamma to be slow, and or maybe high strain rate to maintain small grain size and to allow the thermal runaway. So we are looking for subduction dynamics that can enable these two conditions. These are not strict boundaries, but it's the idea, rather high strain rates expressed at rather low temperature. So what can dynamic models say about that? First, I also want to emphasize that for a long time, the deep earthquakes have only been were thought to be related to the thermal structure, to be controlled by temperature only. It seems to be partly true. We need cold subduction zone, but it's not the only answer. So here I show, this is a recent review map by Zhang in 2020 on the deep earthquake. So the deep earthquakes are in red, deeper than 300 kilometers, and the size of the shape represents the magnitude. So for example, here you have the 1914 Bolivia event. There's a lot of deep earthquake happening in the Tonga subduction zone as well, and in the Japan one. So there are some subduction zones with deep earthquake, but not all of them. You see, for example, Alaska, no deep earthquake there. On the other hand, we have the map of hot versus cold subduction zone that is defined by a parameter called the thermal parameter, phi, that was defined early on when the plate tectonics was formulated by Dan Mackenzie and then refined for the year. So it's phi is the product of the slab age at the trench. So is the age old like here in Japan, or is it quite young like here in South America, times the vertical velocity. So it's the unit is length, and this is age time velocity. So phi is expressed in kilometers. The thing to remember is that the larger the phi, the colder the subduction zone. Hence why the phi is this is a blue scale, blue for high red for high phi, and red for low phi. So you see there is not a total correlation between the two maps. So for example, this large event here corresponds to a low phi, to a hot subduction zone. And we can also see that even though here phi is quite, well, it's intermediate, it's not that low, there is no earthquake at all. However, we still have here for Japan and Tonga seismicity, deep earthquake for cold subduction zone. So it explains some of the events. It seems to explain some of the events, but not all. This is another way of viewing that. So in a paper in 2004, Omori and co-workers, they have plotted as a function of this thermal parameter phi. So this is cold subduction zone, hot subduction zone, the frequency of earthquake. So you see that indeed you don't get a deep earthquake for a very hot subduction zone, but that this was the Bolivia event in 1944. It's not, well, it's not valid forever, because you still have quite a large event even for hot subduction zone. So I also wanted to point out, if you want to find out what are the thermal parameters for your favorite subduction zone, don't hesitate to use the SubMap database. This is developed in Montpellier by my colleagues Serge Lallemand and Nestor Serpa. It's really nice also to use with students while teaching. You can draw maps, cross-section, and do a really nice analysis of subduction zones. Okay, so after temperature, people have proposed that it's not only temperature, it might be also related to strain rate, with the mechanisms suggesting that. So here, for example, you have a depth frequency of diagram of earthquake in the global subduction zone. So we're interested here in the dark gray zone that is deeper than 500 kilometers. And you see that some subduction zones, so Tonga has a lot of seismicity, but some other have no seismicity at all in this deep range. So it's not only about temperature, because we need probably to accumulate stress and to deform at high strain rates. So here is, for example, a sketch explaining why we don't expect necessarily the earthquake to happen inside the cold slab, but maybe in the vicinity where the bending stresses are larger. So this is a 2D view, but also people have suggested that in 3D, since your slab shapes evolve along the trench azimuth, you can also have hoop stresses in addition to bending stresses that could explain the deep seismicity of this deep hinge zone. In a more recent paper, Magali Bilen, so she did some subduction models where she suggests that the bending, the various bending of the slab at depths corresponds to peak in strain rates that can explain the peak in seismicity that are different for every subduction zone. So this is something that has already been on the floor. What can we bring here with the diversity of subduction models? The nice thing about dynamical models is that we have an evolution, a coevolution of both temperature and the strain rate inside the slab, and this is self-consistent. For example, in the early model of Mackenzie, the velocity of the slab is prescribed. It doesn't evolve, it doesn't react to deformation or buoyancy evolution. We also want to test whether the surface thermal parameter that is calculated at present day from the slab age and the velocity, can that relate to deep thermal structure? And also identify if they are, if we can couple both the low temperature and the high strain rate depending on the subduction dynamics that we observe. So the tool I'm using, so it's a thermo-mechanical model. So this is what I used during my postdoc, the finite element cut fluidity. So developed by Rodri here, the AMCG group in London, including Stefan Kramer and also Kyan Wilson. I won't go into the detail, but as Rodri mentioned, there is a nice auto-adaptive meshing that allows us, in particular for subduction zone, to resolve this fine decoupling layer between the subducting and the overriding plates, and so to investigate all sorts of cool features. Here I present a 2D thermomechanical model. What are the ingredients? So I have a 2D box that matches the whole upper mantle depths. And in between the upper mantle and the lower mantle, I impose a viscosity jump. So here it's written 30, but depending on the simulation I will show you, it can be either 10, 30, or 100. Based on gravimetry, it seems that it's more in this order of magnitude, but I'll also show you some simulation with a tenfold viscosity jump. There is no phase transition in this model, so this is one of the simplifications, whereas we think that phase transition play a role in buoyancy and probably in metastability, but here I just want to investigate a mechanical response associated to the large scale folding, not the detail of phase transition. So here the buoyancy depends purely on the temperature. So this is the initial state. The plate will sink because this is denser than what is below, because this is colder than the asthenosphere. And finally, the rheology, so the viscosity dependency that I implement for the material. This is where basically all the sequence ingredients are put. So I have several types of rheology, of viscosity, one mimicking the pseudo-brittle for the surface, one based on the flow dose of creep derived from experiments, so one for diffusion creep and one or two for the dislocation creep, both at low and at high temperature. I insist on this low temperature dislocation creep because here the plate, it's a cold plate. So if you want it to deform, you need a creep mechanism to be able to deform it on the large scale at depth. Something else that we can play on these models to see some various dynamics that I will show you later. We can vary the initial ages of the plate. We can vary so the viscosity jump, I said that, and we also can vary. We can implement a subplate weaker layer, perhaps mimicking melt content or something, but we can play on that to have a diversity of subduction morphology. So let me start by showing you one example simulation. Yes. Okay, so here, so I pose the color scale here, which represents the viscosity. Okay, so it's not only it's not the temperature, it's not the strain rate, but it's a reflection of the two because viscosity depends both on temperature and strain rate. So we have low viscosity here in the upper mantle, in the asthenospheric upper mantle, a higher viscosity in the lower mantle. There is a viscosity jump and the slab will deform when it encounters that. And we have a high viscosity in the plate in red because they are cold. However, you can see already from this image, so the white line are the isosurfaces, that the viscosity is lower when the plate is deformed, here at the bending region. And here the slab is unbending, and you have a low viscosity as well. So this all comes from the rheological parametrization. Okay, so subduction advances, we get some deformation upon the jump, and here it's mild deformation compared to what I will show you afterwards. And the slab sinks quite vertically. There is not much trench retreat, and you see here a high strain rate, a relatively high strain rate and low viscosity when it falls. Let me show you now another behavior. No, not this one. This one. So this one, I'll start from the beginning. So you see the same initial condition, but this time the lower mantle is a bit more viscous, and we have added also a low viscosity subplate layer. The subduction is a bit faster, and you see here some folding forming with very high strain rates when the slab folds. So coming back to the first simulation, the rather vertically sinking slab only deforming a bit. So I analyze at every time step, because I want to have a representative view of this subduction dynamics. As a function of depth, what is the minimum temperature that you can track here? So this is in the slab core. What is the minimum temperature as a function of depth? What is the maximum strain rate as a function of depth? Here it's a strain rate log. You see when it folds, when the slab is folding, you get some high strain rate, even at low temperature. So I track the maximum strain rate, and here my for temperature lower than 1200 K. I also track slab width, surface velocity, and plate age. But first, I focus on temperature and strain rate as a function of depth. So these are diagrams that are a bit hard to read, but I will show them several times. So tell your brain that this is the depth, okay? This is the same scale as here. And here it's the time. So one column here represents one snapshot of the model. This is the minimum temperature. So as a function of depth, what is the minimum temperature at a given time? And we stack that for every time. We see the sinking of the slab. So first it's rather shallow, and then it sinks back into the mantle. You already see here that you have some oscillation in the temperature at depth that are related, I will show that later, to surface velocity oscillations. To the right, you have the maximum strain rate encountered by the slab in the temperature envelope that is quite cold, so here lower than 1200 Kelvin. And you see here that you have some times of high strain rate associated to folding and some other regions of lower strain rate. So it's hard to, it's not that obvious to retrieve some diagnostic of this complex diagram, but we want to be able to characterize one subduction dynamics. So what do? So we focus on the transition zone, like between 400 and 700 kilometers. And for the whole time sequence as a function of depth, so in between 400 and 700 kilometers, we use a box plot. In French, you say a moustache box. So it's rather elegant. So a box plot here, for example, of the minimum temperature. So of course, you see the minimum temperature increases as a function of depth, because your slab is heated up both by the lithospheric on both sides. So as you go deeper, your slab cold core temperature increases. Okay? We can do the same for strain rate. So for strain rate, we select only the region between 400 and 700 kilometers. You see that anyway, below the viscosity jump in the high viscosity mantle, the material doesn't deform much. The strain rates are quite low. And for each depth, as a function of time, we again plot a moustache box, a box plot with the different percentile here. So we can see that we have quite high strain rates above the viscosity jump, between 500 and 600 kilometers, so above the viscosity jump, where we feel the folding, and quite low below. So we chose as diagnostic numbers, we take for the thermal proxy the minimum temperature at 550 kilometer depth. Well, I could have chosen 500 or 600, but here I will just show the result for 500 kilometers depth. And here, for the deformation proxy, I take the maximum strain rate, still in the colder region, at 550 kilometers depth. So once again, this is above the viscosity jump that we impose. And of course, it depends at which depth we think the viscosity jump are, but in these models, it's at a constant depth. So for a whole subduction regime, I'm then able to put my slab in this diagram as a function of the thermal proxy and the function of the deformation proxy. And I'm interested in the subduction regimes that will fall into this quadrant here of low temperature, but of high strain rate. So I took the arbitrary limits of 1000 Kelvin and 10 to the -5 second -1. Of course, we can discuss where it is laterally and vertically as a function of the mechanism, but it's the general idea. Okay, so I show you this for one subduction regime, but now I will show you that for a lot of subduction regimes. However, I first want to justify why do I pick a lot of subduction regime? Isn't subduction just a slab sinking down and that's it? Actually, we think there's quite a lot of different subduction regimes. So the first argument comes from seismic imaging. So this is a review by Saskia, who's showing the various morphologies of slab, flattening, penetrating, more or less inclined, bending, etc. So not every subduction is unique, and not all the slabs have the same morphology. This is what we see at present day. It has also been suggested that there's quite a lot of folded slab because some of the seismic imaging reveal fast anomalies larger than 300 or even 500 kilometers. So they're termed slab walls. Okay, so it's not just a plate of 100 kilometers sinking down and thickening a bit by diffusion. It has been suggested that indeed these slabs are folding and piling. So this is a different regime to the one I show you first with the small deformation. Okay, this can be confirmed, and this is another great tool that is nice to use with students, submachine. We can see also that at a given depth, so for example here just below the transition zone, the width of the slab, it's not the same for all the subduction zone, okay? It varies quite a lot, so this is an argument saying that not all subduction zones have the same dynamics. And so this has been reproduced a lot in dynamical models. So this was the work I did during my postdoc more than 10 years ago already. So defining different regime. So the fast sinking slab that then exhibit a large trench retreat, the slab that was horizontally deflected, the slab that was folding vertically. So a variety of morphology that I achieved in my model by changing the initial plate edges. But this was really the proxy for different forces. So how much your slab is deforming, how fast is it sinking, how much is the upper plate resisting, or the trench is resisting deformation as well, and so hampers trench retreat. What is the magnitude of the viscosity jump? So we could draw a subduction regime diagram depending on various parameters, but justifying that yes, it's not. We understand why we have such a diversity of tomographically imaged slab shape, because subductions have different trench and plate velocity history, and they didn't initiate at the same age either. So modelers love to draw regime diagrams. So I was not the first. It has also been shown that subduction dynamics depends a lot on the viscosity contrast between the plate and asthenosphere, or the initial thickness of the plate, in analog experiments and in theoretical model. Also, you can have a proxy. How much does it depend on the slab buoyancy? And this will be influenced by phase transition as well, of the stiffness of the slab. Okay, so always these different modes, different regime, vertical folding, retreating, flattening. It also depends on the slab width. So here, for example, depending on age and width, you get different regime, but you also get different trench curvature types. It depends on the wick layer. So you see when you vary the wick layer, you can end up with large scale folding or smaller scale folding here for older plates. And it depends on a lot of stuff. It depends on phase transition as well. So here you can see you can obtain a flattened morphology, but that exhibits a lot of folds as well. Depending also on the decoupling that you implement for the crustal viscosity, depending on the radial viscosity structure. So for example, do you put a viscosity jump at 660 kilometers as I did, or do you spread it out over a thicker transition zone? So you can really have a diversity of slab morphology. Here, I'm not investigating all of them. I will just show you a collection of, so I showed you already this first slab, slab A, this one who exhibit a large scale folding. This one horizontally deflected, this one is a bit different. So, well, this one is inclined and strong retreat. So for all these slabs exhibiting different subduction dynamics and morphology, where are we? In terms of, okay, I will come back later to that. Where are we in terms of temperature evolution with depth and time, and strain rate evolution with depth and time? Okay, so this is the same plots I showed you before. So you see this one is hotter, this one is colder, this one is more deforming, this one is less deforming. But if we summarize this by putting them in the diagram, this is what it looks like. So once again, this is the thermal proxy with two hot slabs, maybe, for the mechanism proposed. And here, this is the deformation proxy. And at the bottom of the graph, with slabs that are not probably deformed enough to accumulate enough strain for an earthquake. So what you see is that even though the slab that I show you, sorry, which one did I show you? Yeah, the slab that I show you first was probably not that far from the temperature limit. It could have been cold enough, but it's still not deformed enough. Conversely, other slabs are deforming quite a lot. For example, slab D here. Oh, sorry. This slab or this one, they are deforming quite a lot, but they are rather hot. You see the isotherm do not go very deep here. So the two slabs that seems to be both cold and rather deforming lot are this one, the inclined strong retreat, and this one that exhibits the large scale folding. So this is why we suggest that large scale folding, this slab C here, large scale folding is really your best chance to get both low temperature and high strain rates. So here you see the strain rates are quite well, almost up to 10 to the minus 14 second minus 1. But I will come back to this slab C here, so the large scale folding, because we saw that it wasn't that easy to predict the thermal structure at depth. So here, oops, sorry, yes. So here, these are just snapshots evolution with the isotherm view of the folding of the slab through time. And you see that if at first here you have the classical isotherm shape and you can say, okay, this looks like the advection models and maybe the phi parameter is quite good here. In the transition zone, you see the isotherm here. It's not completely dictated by the surface. It depends on the past thermal structure that was already there. And we confirm this by calculating. So for these models, we have can calculate both the trench, the plate age at the trench. We can calculate the evolution of the surface velocity. This is the red curve here. And so we can calculate the thermal parameter, which is the slab H times the vertical velocity. Sorry, I didn't put it here, but I can calculate also the sinking velocity through the dip or through the slab tip velocity, doesn't matter. So we can compute the evolution of the thermal parameter at the surface. And this evolution, then we can try to predict from this surface evolution, we have the phi, what should be the temperature at depth. And then we compare it to the actual temperature that we get. So we have a temperature predicted from phi, from the surface phi, the instantaneous phi, and we have the actual temperature at depth. And this is what we see. So this is at different depths, 250 to 800 kilometers. So in blue, you have the simulation temperature. So this is what we observe in our numerical experiments. And in the dashed line, you have the one predicted from the surface temperature. And what you see, so it's the right order of magnitude when you're quite shallow. But as you go deeper, you will see a temporal shift. Okay, you will see a temporal shift between the high surface velocity and the high temperature. So at 250, it's not really visible. But then as you go deeper, you see that this shift increases. So there is a temporal delay. Here it's several million years, depending on the depth, between what you can predict from the surface, the dashed line here, and what you actually observe in the model. You also have, as a consequence, a temperature offset between what you can predict here and what you actually observe in the experiment. And this temperature offset can be up to, can be more than 100 Kelvin, which is quite important when you're talking about dehydration or other mechanism. Yes, so this is a complicated way to summarize, but we've seen this plot already. So this is depth and this is time. And you see that, so this is the phi that I can calculate the other way around. I have my temperature at depth, sorry. I have my temperature at depth from the model, so I can calculate a theoretical phi at each depth and at each time. And you see that the phi that I calculate as a function of depth, actually, it's related to the oscillation in the surface velocity of the model, which means that at depth, I have a delay corresponding to the sinking velocity of the slab, so 5 to 8 centimeters a year in the upper mantle. And here it's a slower delay. It's about 1.2 centimeter in the lower mantle. Okay, so it may not be, it may be only a few million, a few tens of millions of years, but there is still a delay between the surface prediction that we made today and the actual thermal structure at depth. Okay, so these are my conclusions. So the temperature in subduction zone deeper than 300 kilometers, it's more related to the past thermal parameter than to the present day one. So if we take, if we consider a sinking velocity of 2 to 5 centimeters in the subduction zone, it means that maybe we have to check also the thermal parameter in the past from 10 to 30 million years ago. That's the first thing to take away. The thermal parameter calculated from present day value has no reason to reflect the deep, the deep thermal state of slab in the transition zone. My second message is that also we saw that the folding mattered a lot for the thermal structure, especially when you're near 500 or 600 kilometers. So the idea is, can we have a proxy for the folding of slab? And this is the work by my colleague Nestor Serpa, who proposed this KR, the kinematic ratio, to try to evaluate how much slabs are folding with here, so quite a lot of folding, even though this is a cold region for, sorry, even though this is a hot subduction zone. So it seems important to evaluate the past folding of slabs, because folder slabs could be more prone to deep focus earthquakes since they have both low temperature and high strength. Okay, and with that, I thank you.
Fanny, great talk. Any questions? Yes.
What do your colleagues who work on deformation mechanisms and potential mechanisms that trigger those quakes of depths, what do they think when they see the models? Well, is that is that something that they think could be compatible with what they see in the lab? Is that something basically they think that the physics that's in your model is sufficient, or do we need more?
Yeah. So for example, here I mentioned the mechanism of thermal runaway, and when I showed my strain rate diagram to this colleague, so Marcel Tillman and more recently Arnaud Schwang, they say, oh, you see here the 10 to minus 15, it's at the lower end. So they say, oh, it's quite low, your strain rates. I'm not sure that we would be able to trigger the thermal runaway. The temperature is fine, but the strain rate might be a bit low. So this is also why I didn't mention it explicitly, but one of the simplification in my model is that it's purely viscous, meaning that you can't, you don't store strain. The strain rate, sorry, you're not looking at strain accumulation. So whereas having maybe perhaps a viscoelastic rheology might help to increase strain. I also have to mention that adding phase transition, so with additional buoyancy, that would increase the sinking velocity, and you have the viscosity jump that would resist it, could result in a higher differential sinking velocity, so a higher strain rate as well. But basically, the coupling here, it's not, we're not ready yet, because we have, even in our highly deforming slab, it's maybe still a bit too low for this small scale models.
For your slab lithosphere, did you vary? What parameters did you vary for the crust or for the top of the slab, or is it a uniform?
Yes. In all the models I showed, well, in our models at least, this crust here, this crustal here, so it has a minimum, it has a maximum viscosity. So it's capped at 10 to the 20 pascal second. It can't go higher, sorry, but it can be a bit lower because it has its own pseudo-brittle rheology with a lower friction coefficient, otherwise it does not work. And also it has its own dislocation. And this may matter if I look at this regime diagram. So you see here, if you have a stiff crust, you will likely, how do I phrase that? If you have a stiff crust, you're more likely to penetrate and have a vertical descent. So this would mean probably more deformation at some points. Whereas if you have a weak crust, you retreat more, and then you have a long-term stagnation. Yes, so it matters indeed.
Yeah, I was thinking about how much water or fluids you can get into the crust. So the paper is written about earthquakes in terms of hydration state because of how much water you can get into the slab to generate these earthquakes.
Yes. Yeah, so it would be a question. So I didn't vary the thickness, but you could also thinking of vary the thickness or vary the viscosity, saying there is more or less water. It's also a question like how much do you dehydrate below the arc, quite shallow, and how much can you transport more deeper? So probably, not sure, but probably that most of the water that would be in the transition zone would come from hydrated mantle serpentines rather than chlorite or crystal material.
Yeah, and I was also thinking of the bending fault before in the fork and how much water you can get in.
Yes. In the outer rise faults and yes. So how much water do you get, which will then probably have an influence on the viscosity? Another question mark. Let's build a regime diagram.
Thank you for the talk. I was wondering, you showed the locations of the deep earthquakes and the distribution on the map, but you didn't show more on the focal mechanisms, for example, or source time functions, or maybe the proximity of these large events. And I'm wondering if these additional parameters would be useful and how useful they would be. You can maybe expand on that.
Yes.
So in other words, like a new generation of earthquake catalogs, what should they contain to help constrain our research?
Yes. So sorry, I should have put that as a supplementary slide. Yes. So here, for example, it's a paper by Jakub Pokorny and Hanna Chiskova, who is also doing subduction models, and they're interested in the Tonga subduction zone, where, as you said, the focal mechanism, they show different directions of tension and compression axis, and they try to relate that to is it bending or unbending, because they didn't have the same location, and their conclusion was that yes, depending on the slab morphologies that you can achieve with models, you will not get the same focal mechanism at these different parts, so that can be an additional constraint. So you're right, it's not only about, if I take the catalog here again. It's not only about the depth and the magnitude of the earthquake, but also the focal mechanism, and I would say also the distance to the coldest core, to where we think the coldest core is, because then it might be either really an intraslab earthquake related to metastability or something more related to the hinge, and then but we would expect, I would say, only meaningful focal mechanism for these authorized earthquakes that are really related to bending or hoop stresses, whereas here, I'm not sure that focal mechanism would mean something if dehydration reaction are the trigger to something.
How about the source time function itself? So how the energy is actually released?
Oh yeah, this I wouldn't know. So I'm happy to hear your comments on that.
Okay, we've got time for one more question, and we can carry on questions at easy.
I'm interested in why that some subduction zones don't have any deep focus ones, why they're mostly intermediate. Do you have any sense of why that is? Like the ones you like on the slide before, I think Alaska. Yeah.
Yes, sorry. Yes, Kamchatka, Kuril, yeah. And yeah, well, sorry, yes. Alaska and Kamchatka here, and Mexico as well. Well, you could think of different reasons, because Mexico is where the slow slip events are. So is there something releasing stress up deep in the slab? And so, well, so...
There's nothing in the slab
morphology. I think there is also the 3D structure issue. So if I come back to this map, well, No, not for this one, but here, for example, it's a rather there's a complex 3D morphology, the same in the Marianas. Yes, so I would say that maybe the stress state at depth depends also on what happens on the edge of the subduction, so it's more variable through time. So yeah, so maybe something related to 3D, but it's good that we started with 2D models so that now we understand the basics. But yeah, this it's a good question, and other people are working on it.
Yeah.
Luckily.
All right, so let's thank Fanny one more time. A few quick things. Apparently, we have afternoon tea outside, all free. The only rule is that you need to put your dirty cup in the dishwasher, so please remember to do so. Second point, Fanny's around for another month. If anyone has any questions, she's going to be sat next to the Ringwood room in Jacob 4. Is it 4? Jacob 4.
Yeah.
Yeah. So thanks again, Fanny.
Thank you.